So hello and welcome back to the discussion on heaps. In the previous video we've seen what is a binary heap, and we have seen several operations which can be done in order log n. We could build the heap in linear time, but we said that so we are not able to do merge in time which is faster than linear time. So in this video we are going to study binomial heaps, in which we will be able to do all the operations with the same complexity of binary heaps, but we will be able to do the merge or union in order log n. So in the case of binomial heaps, we first define what is a binomial tree. That gives you the structure of the tree, which ensures nice property like bottom of PP5 to be in order log n, and several other properties. And so we also need to maintain heap property, which is if you look at, since we are discussing the minimum heaps, the value of a node is always smaller than or equal to the value of the children. So there are two things that we are going to define. So the heap property will remain same as in the case of binary heaps, but the structure of the tree is going to be different. The structure of the tree in the case of binomial heaps is a collection of binomial trees satisfying some property. So before we talk about this binomial heaps, we'll talk about what is binary trees. We'll first define what is known as binomial trees of a particular order, look at some of the properties of this, and then we will define so what is a binomial heap in this video. So the binomial trees of order k is defined inductively, so, and it's denoted by b of k. So we'll start with b of 0. So b of 0 is just one node, and b of k is constructed by taking two copies of b of k minus 1 and making one as the child of the other. Pictorially it looks like this. So you take two copies of b of k minus 1, so this is a binomial heap of order k minus 1. You take another copy of binomial heap of order k minus 1, so make one as the left child of the other, right? So this has been made as the left child of the other one, so this entire thing will be called as b of k. Let's look at an example. So b of 0 is just one node, so b of 1 is you take two copies of, this is a b of 0 and this is another b of 0, just make one as the child of the other one. So b of 2 will be, so this is one copy of b of 1, you took another copy of b of 1 and made as one as the child of the other one. So if you repeat this, you get b of 3, right? So this will be so one, you basically take two copies of b of 2 and make one as the child of the other one. In general, so b of 0 is defined as just one node, and in b of k we take two copies of b of k minus 1 and make one as the left child of the other. So this is called as the binomial trees of order k. Now let's focus our attention on some of the properties of the binomial trees. Let's say that I delete this particular node from B3, I take B3 and delete this particular node. So if I delete this particular node, I also delete all the links which is connected to this. So what I get is, so if I just ignore this, I get this. So I took b of 3 and I deleted all the children of 8. You see that this is b of 0, this is b of 1, and this is b of 2. So if I take b of 3 and delete the root node, the children of 8 is basically b of 0, b of 1, and b of 2. So this continues, this can be generalized. If you take b of k and you look at the children of b of k, so you get exactly one copy of b of 0, b of 1, b of 2, b of 3, and so on, and till b of k minus 1. So essentially b of k has exactly k children. When you see it from the right hand side too, when you traverse the list from left to right, you basically get b of k minus 1, b of k minus 2, b of k minus 3, and so on. You basically get all the binomial trees of order less than k. So this is one important property. We will use this property sometimes later. Let's look at other properties of these binomial trees. If nb is the number of nodes in a binomial tree of order k, then the claim is that the number of nodes in b of k is 2 to the power k. Again, the proof is by induction. If k is equal to 0, then n of b of k will be 2 to the power 0, which is 1, right? So if k is 0, then the by induction b of 0 is just one node, right? So if k is 0, then the number of nodes in b of 0 is 1. So by induction, we will assume that n of b of k minus 1 is 2 to the power k minus 1. Then we notice that n of b of k will be 2 copies of n of b of k minus 1, right? So b of k is basically 2 copies of b of k minus 1. So the number of nodes in b of k will be exactly equal to the number of nodes in k minus b of k minus 1 and the number of nodes in b of k by k minus 1, right? So by definition, right, so the number of nodes in b of k minus 1 by induction will be exactly equal to 2 to the power k minus 1, and this is also equal to 2 to the power k minus 1, which is 2 into 2 to the power k minus 1, which is exactly equal to 2 to the power k. So this implies that the number of nodes in a binomial tree of order k is exactly equal to 2 to the power k. Now let's focus on the height. If h of bk is the height of the binomial tree of order k, then the height of b of k is exactly equal to k. So if you look at the height of this node, height of a node, height of a tree is the height of this particular node. So this will be 1 plus height of his maximum height of his children. So it has the child which is b of k minus 1, right? So the height of so this is the one which has the maximum height, because all the other ones will have a order smaller than b of k. So the height of b of k will be exactly equal to 1 plus height of b of k minus 1. But by induction, we can assume that height of b of k minus 1 is exactly equal to 1. Is exactly equal to k minus 1, and you are adding 1 to this. This essentially means that height of b of k is k. So height of b of k minus 1 is k minus 1 plus 1, because height of b of k is exactly equal to 1 plus the height of b of k minus 1, right? So you can also verify that if k is equal to 0, then height of single node is 0 by definition. So now let Lk of I be the number of nodes which are at level I in b of k. I repeat, Lk of I is the number of nodes which are at level I in b of k. Then the claim is that this number should be exactly equal to k choose I. Let's look at this example. So in b of 3, so this should be b of 3. So this is a node at level 0. So level of a node is defined as 1 plus the level of the parent. So these 3 nodes have level 1, these 3 nodes have level 2, and this is the one node which level 3. So if you look at the number of nodes, if it is a level goes from 0, 1, 2 and 3. There is one node with level 1, there is 3 nodes at level 1, and there are 3 nodes with level 2, and there is exactly one node at level 3, right? So the number of nodes which are at level 0 is exactly equal to 1, which is the root node. So now if you look at so the order of this is 3 choose 0 is 1, 3 choose 1 is 3, 3 choose 2 is also 3, 3 choose 1, 3 choose 3 is again 1, right? So so the number that you are looking at is exactly equal to 3 choose I, where I is the level of the node. So let's look at the proof of it. So the proof is again by induction and k. We will assume that this theorem is true for all the k's which are strictly smaller than k, in particular k minus 1. Then we will try to see that Lk is equal to k choose I. Now let's just ask the question, if I have to just look at b of k, so what are all the nodes which are at level I? So if a node is, the level I nodes can kind of either come from this part of the tree, or it can come from the this part of the tree. So notice that level of a node here, if for every node in this part of the tree will not change after the merge. But if you take any node in this tree, the level of a node will increase by 1 after we merge this with the other b of k minus 1. So if I have to compute, look at all the nodes which are at level I in b of k, I have to look at all the nodes which are at level I in this part of the tree. and I minus 1 in this tree, because after the merge all the nodes with which are at level I minus 1 will be at level I. So the total number of nodes in B of k which are at level I will be exactly equal to, just look at all the nodes which are at level I in B of k minus 1, that's this part of the equation, and you just look at all the nodes which are at level I minus 1 in B of k minus 1. So this is the sum of these two. Since the induction is true for k is equal to k minus 1, this number is equal to k minus 1 choose I plus k minus 1 choose I minus 1. If we expand this, we will show that this is exactly equal to k choose I. If we expand this, so what we get is this is factorial k minus 1 divided by factorial k minus I minus 1 into factorial I plus factorial of k minus 1 divided by factorial of k minus I into factorial I minus 1. So what we are going to do is that we are going to take this factorial k minus 1, which is a common term in the numerator. In the denominator we will take factorial k minus 1 here and factorial I here. So what I have here is factorial k minus I, but if I want factorial k minus I have to multiply both numerator and denominator by k minus I. And in this part what I have is factorial I is what I need, but what I have is factorial I minus 1, so I have to multiply both numerator and denominator by factor I minus 1. So if I add this up, this is k minus I plus I, so this is exactly equal to k when you multiply with the factorial of k minus 1. So what you get is factorial of k divided by factorial of k minus I into factorial of I, which is exactly equal to k choose I. This completes the proof by induction. So if you take B of k and if you look at these the number of nodes which are at level I, then this is exactly equal to k choose I. These coefficients are called binomial coefficients. If you look at the expansion of x to the x plus y to the power n, so you get it as summation of x to the power I, y to the power n minus I, n choose k, right? So these coefficients which are as in the binomial expansion, these coefficients will look like k choose I. These are called binomial coefficients. So this is precisely the reason why these trees get the name binomial heaps, binomial trees. So in summary, we have defined so B of k to be two copies of B of k minus 1. One is the left child of the other one. This is the binomial trees of order k. Then we have shown that the number of trees in B of k is exactly equal to 2 to the power k. Height of B of k is exactly equal to k, and the number of nodes which are at level I in B of k is exactly equal to k choose I. And if you look at the children of B of k, they are essentially copies of B of 0, B of 1, B of 2 and B of k minus 1. We will use all these theorems when we construct binomial heaps. Now let's pay our attention to what are binomial heaps. Binomial heaps is a collection of binomial trees such that for each order there is at most one copy of B of k. It's a collection of B of k's, but duplicate B of, for example, B of 2 can appear at most once. Either it may appear, it may not appear, but you cannot have two copies of B of 2. So, and in each node, this is a collection of binomial trees, and in each node we will have some value associated with the node, and in each node the heap property is satisfied. Since we are talking about the minimum binomial heap, so value of a node is always smaller than or equal to value of every children of it, right? So that's what makes it as a heap. There is a structural property. Structural property is a collection of binomial heap is a collection of binomial trees, so that in each order there can be at most only one copy of B of k for a particular order, and in each of these nodes of the binomial heap the heap property should be satisfied. Let's look at an example. This is an example of a binomial heap. There is a B of this is a copy of B of 1 and this is a copy of B of so this is a copy of B of 1 and this is a copy of B of 3, right? So if you look at every node, so let's look at 34. So 34 is smaller than 46 and 42. 46 is smaller than 83. 7 is smaller than 92. So if you take any node and you look at the children of it, so the value of a node should be smaller than or equal to value of the children. If this property is called as binomial heap property, and if you look at any tree, any node in the collection, this property should be true, right? So we are only remember that we are only comparing a node with its children's value, right? So we will not compare a node with the values of some other node in some other tree, right? So we will only look at the particular children's of that particular node and then compare it to its value. So the heap property should be true at every node. So the question is, if I give you 100, is it possible to construct a binomial heap with 100 nodes? Because there is a strong condition that you have to take a collection of BFKs, but there should be no repetition of BFKs. You can only take at most one copy of BFK. If this condition was not there, I could have taken 100 copies of BF0, because each copy has one number. If there are 100 nodes, then it makes it a node of 100 nodes. Okay, so here is a nice property. So given n, there is always a binomial heap with n nodes. Which of the BFK that you should be taking is decided by the binary representation of n. Let's say, for example, if you give me 1101 011 as the binary number, then I take a copy of BF0, I take a copy of BF1, I don't take a copy of BF2, I take a copy of BF3, I take a copy of BF5, and I take a copy of BF6. Okay, since this is a binary number, so every binary number can be written as summation BFI into 2 to the power I. So the BFI is either 0 or 1. So if BFI is 1, then you take a copy of BFI. If BF0, then you don't take a copy of BFI. Right, so this is so now if you look at the sum of all the numbers here, right, so if you take BFI, you know that the number of elements in BFI is 2 to the power 5, right? So this entire number can be written as sum of BFI into 2 to the power I, where BFI is either 0 or 1. If BFI is 0, then I don't take a copy of it. If BFI is 1, then I'm taking a copy of it, and in that particular tree, so notice that this is a tree, this is a binomial tree with order 3. So in general, if it's a BFI, it will have exactly 2 to the power I number of elements in it, right? So given a n, so if you are asked to build a binomial heap with n number of nodes, what you need to do is that you have to look at the binary representation of n, and wherever there is 1, that's such an order BFI. If BFI is 1, then you have to construct a you have to consider a binomial tree of order I, right? So that is so it's always possible to construct a binomial heap with n number of elements in it. Now let's look at the structure of the binomial heap. So it's a collection of binomial trees. That means that it's a set of trees. Set of trees can be represented by a linked list. So you take BF0, BF1, BF3, BF6, BF5, BF6, BF12, and BF61. This is an example of a binomial heap. All these nodes, so each of them is a tree. So what I have represented here is only the root of the tree, and this is a BF12, right? So it's a copy of BF12. There will be 2 to the power 12 number of nodes in this, and you know the structure of BF12. Okay, so now so this entire root of each of these trees is connected by a single linked list. You can also imagine that this is a circular single linked list, right? So you can, so this last node is also connected back to the first of. When I say that I give you the binomial heap, I'll also always give you the head of the list, right, which is, it will point to the lowest order, and we will also assume that when you go from left to right, order of the trees are in the increasing order, right? So once you reach the last node, if you want to come back to the head of the tree, you can just take the next pointer, will come back to BF0. This is a circular list. We will call it as a root list, right? So this is a circular single linked list, or this list is arranged in such a way that when you go from left to right, you see all the binomial trees whose orders are strictly increasing. I'll also have another pointer that I'm going to maintain, which I call it as minimum pointer, which will point to a node which has the minimum value. Because of the heap property, in any tree, the minimum is always at the root of the tree. So the minimum in the binomial heap can be in any one root of the collection of trees that it has, right? It can be anywhere. So whichever tree has the minimum number among all the numbers in the root list, that's where the minimum will point to. So this minimum pointer is important because if you want me to give you the minimum, in the case of binary heaps, I had to just report the root node, right? So in this case, the minimum pointer will help us to identify the minimum node in order 1, right? That's precisely the reason I'm maintaining an additional pointer, which is the minimum. And in each node, we have the following structure. In each node, we will have the value of the node. So the pointer to the next node in the root list. So if I have to traverse the list, I need the pointer to the parent. And this is, each node is a tree, right? So it's part of a tree, so there should be a pointer to the parent. If it is, if it's in the root list, then the pointer to the parent is a null pointer. Then each node has a certain number of children. So not necessarily, this is not a binary tree. A node can have more than one child. So there will be a child list, which is again a linked list, which will give me the pointer to all the children of this node. Okay. Then I also have an integer which will give me the number of children of that particular node. So all this information is available in each node of the binomial heap. That we also want to look at so what is the complexity, what is the number of trees that we can have, and what is the height of each of these trees. The number of nodes in the root list is exactly equal to the number of ones in the binary representation of n, right? So because I said if I have to look at the binary heap, so of an n with n number of nodes in it, what you have to just look at is the binary representation of that n, and wherever there is a 1, you take a copy of BFI of that. So the number of trees in the root list is exactly equal to number of ones in the binary representation of n, and the number of ones can be at most n, log of n, right? So the number of nodes in the root list is order log n. So if you want to traverse the list root list from left to right or right to left in any order, since it's a singly linked list, you can only traverse in the forward direction. So traversing the list in one direction will actually take at most log of n time. So then height of a binomial heap is the defined as the maximum height of any node in the binomial heap, right? So the maximum height will always be at root of one of these nodes. Now if you look at B of k, which is a binomial tree which is part of this heap, so the number of elements in B of k is 2 to the power k, and since we are talking about the binomial heap, the n number of numbers, the 2 to the power k should be smaller than or equal to n for any binary tree, binomial tree which is part of this heap, right? So because I am talking about a tree with n number of nodes, so if you take any binomial tree which is part of this collection, total number of nodes there should be smaller than or equal to n. So if I take a binomial tree of order 2 to the power k, then we know that height of this tree is exactly equal to k. Okay, so if you take any tree in this collection, the height of this tree should be certainly smaller than log of n, right? So we can so the height of this tree is going to be at most log of n. So in this video we have seen defined what's a binomial tree of order k. Then we have seen some properties of binomial trees of particular order. Then we have defined the binomial heaps to be a collection of binomial trees with the condition that you can have only one copy of a particular order k, right? So then we have also seen how to represent these trees, what are the structures that are required to represent binomial heaps. In the next video we will come back and see what are the operations that we can do efficiently on this binomial heaps.